The first item of business today is to decide when the midterm is going to be. The available choices are the Wednesday before spring break and the Friday before spring break. And we shall decide by vote. How many of you would prefer to have it on Wednesday? How many would prefer it on Friday? Wednesday overwhelmingly. Okay, so that's what it will be. Okay, Wednesday before spring break will be the time of the midterm. Excuse me, question? Yeah, it'll be during class time. And if you go to the VSpace site and look under exams, you'll see a whole bunch of prior midterm exams there. I was told many years ago that the way to get a good grade in this course is to do all the previous exams, and that this was kind of a trick. And if so, I think the trick may be on you, because frankly, if you can go back and do all the previous exams, and you know how to solve all the problems in all the previous exams, you've learned just about everything I hope you learn in this course. So that is the best preparation for the exam. Okay, are we? Still haven't figured out the light switch front. Try this one. Okay. We don't seem to be on yet. This says we're on. Why do I have nothing on the screen? This is connected. This is connected. Now let me try redoing it here. I do not know what the problem is. Well, try turning it off and on again. There we go. Okay. When in doubt, check the plug, as they say. Okay, we're talking about defects in crystals, which we organize by dimension. Last time I went over line defects, dislocations. I'm going to review that. That is one of the more difficult concepts for whatever reason for people to get straight. They're harder to see, frankly. And so let's review what dislocations are all about. The real importance of dislocations is the control of plastic deformation in crystalline solids. When crystalline solids deform, they actually deform, as you can see by examining them closely, by the slip of planes of atoms over other planes of atoms. Even in tension, if we pull on a sample in tension, the actual deformation that will happen is the sliding of planes of atoms on planes that are angled to the axis of the load, as shown here in the picture. And as you can see, if I slide the left-hand side of the crystal over the right-hand side of the crystal along a plane that is angled to the axis of the load, the sample actually gets longer. In fact, in a true pencil test, we'll get some slip like this, some like in the opposite direction, making kind of an X, so the sample will get longer uniformly. Well, how can that kind of slip happen? Oh, this is just, I showed you this last time, this just shows you those slip lines in a sample pulled in tension in this direction. If you look at what happens in the inside of a material when that goes on, and this is an indentation, deformation by indentation, per the movie I showed you last time, what you discover is coincident with the deformation, the forming of this indentation pit, for example, you see the development of a dense network of dark lines within the material in this transmission electron micrograph. What those dark lines are linear defects. What you're imaging in the electron micrograph is the local distortion, the crystal strain in the periphery of those little defects. These are the dislocations. In fact, we knew about dislocations long before we knew how to image them. Or maybe the first pictures of dislocations were taken late 1950s, early 1960s. The dislocation theory was developed back in the 1930s. But now we can see the dislocations and follow their behavior. Well, what are these dislocations? Well, if you look at these dislocation lines in a crystal that has been deformed, you see they're very irregular, they're curved, they're kind of tangled up with one another. But they're not simple and straight. However, to understand them, we look at idealized cases in which the dislocations are actually rather simple. The simplest kind of dislocation, and in many ways the most important, because it's what governs this kind of planar slip, is what's called an edge dislocation. Suppose we cut a material, displace the over part of a plane on which slip is going to occur. We imagine displacing the top of that plane over the bottom by a vector b. The boundary of that plane, there will be an accumulation of material. If we now weld the top and the bottom back together in such a way that there's material continuity or crystal continuity across that plane, we can't see anything. All we can see is the linear defect where the extra material is gathered at the front of that slip region, and that's what we call an edge dislocation. The slip, B, is perpendicular to the line of the dislocation. So it's called an edge dislocation. In cross-section in a simple cubic crystal, it looks kind of like this. Here we have the region, here we have the slip plane, the region that has been slipped, the extra material. So there's an extra half plane of atoms, shown here in 3 dimensions, that terminates here in the dislocation line of what we call an edge dislocation. In order for this process to work, the slip vector, B, the amount of slip we get, must be a lattice vector. It must be precisely the edge of some interatomic spacing, so that after the slip is done, we can connect the crystal back together again, and there's no discontinuity across the slip plane. As I mentioned, and we'll return to later, there's such a thing as a partial dislocation, in which there is a discontinuity. But the real slip dislocation, the slip vector B, is a lattice vector, so that these planes come back and match together. When that's the case, the only thing that is left is the dislocation line itself. I could have created this dislocation by compressing the top of this crystal this way, by compressing the right-hand top of the crystal in the opposite direction. There's no way to tell, just looking at the dislocation, what process I used. Question? If you were to hammer it and it were ductile metal, you would leave mashed stuff, and there would be lots of dislocations associated with that mashed. We'll talk about fracture later. Okay, dislocations govern plastic deformation. They can participate in fracture, but that's a very secondary consideration. Fracture is a different thing. You know, one of the great scientific questions that we are still trying to resolve is, do amorphous metals deform via discrete dislocations, or do they deform in a more global deformation process? If you know the answer to that, publish it immediately. Okay, the evidence is ambiguous, but it's actually tending more and more toward amorphous metals do not deform by linear defects, but more volumetric processes. I'm actually not going to talk about, well, I may briefly talk about that later on in this course, but it's not something that's all that well understood, so it's not a good subject for an introductory course. I'm having all kinds of electronic problems today. Try again here. Is that going to work? Doesn't seem to. Okay, we'll try this. Okay, there we go. See if I can avoid tripping over the wire. This is not a very good configuration that I have here. There are two ways to understand dislocations, and it's kind of important to think a little bit about both ways. One way to understand the dislocations is just as a linear defect, as I've been describing it. In that case, the dislocation is described by its line, where does its line run, and by the Burgers vector, or the slip vector that it carries. Another way to understand a dislocation, which can be a very useful way, as we'll see in just a moment, is to recognize that the dislocation is associated with a slip on a particular plane, and the dislocation is the boundary of a region that is slipped. This edge dislocation can be visualized as just the outer boundary of this region that is slipped. The actual deformation by the motion of an edge dislocation we covered last time, and it's fairly easy to visualize. As I move this dislocation forward, perpendicular to itself, recognize that this bounds a region that is slipped. So the region that is slipped, the area that is slipped, keeps increasing and increasing and increasing. If I move the dislocation, sweep it all the way out of the crystal, the net effect is that I have slipped the top of the crystal over the bottom of the crystal by that vector B. Understand the reverse, I'll pick up in a second. The reverse process also works. If I move the dislocation this way, I increase the region that by my definition is not slipped. And moving the dislocation all the way out of the crystal in this direction will restore the original shape of the crystal. So the motion of the dislocation perpendicular to itself causes slip. Question? Would that cause any deformation or stress on it, like for shear, like moving it? Well, you're going to have to do something to make the dislocation move. We'll return to this later in the course when we do plastic deformation. But this dislocation, I mean, just look at it here. You know, in order to move it, I've got to kind of distort things around it. So there's always going to be a stress required, a shear stress, like this, required to get that dislocation to move. And we'll discuss that in much more detail when we get to mechanical properties. The other idealized kind of dislocation is a screw dislocation. Question here. You're talking about in this picture or the previous one? Yeah. Mm-hmm. Well, there's extra material. There's extra material here and here. Now that extra plane has been transmitted to the surface. When you see a slip step, it actually takes a great many dislocations to create a slip step that you can see in the laboratory. But that slip step is a step. There's physically material. There's a discontinuity there. Extra material has been moved out of the surface. And when you see a step, for example, on the edge of an indentation on a polished surface, which you can see in the lab if you look closely, that's what you're seeing. You're seeing this step. Exaggerated, of course, because the step I've drawn here is only one atom layer high. You wouldn't be able to see that. But you get many dislocations moving on the same plane, and this will build up to a macroscopic step that you can see. Okay? Well, now this is a screw dislocation. Screw dislocations, it's the same thing. It's not particularly complicated, although people tend to think it is. In this case, we take our half plane, and we now make our displacement, instead of making it perpendicular to the dislocation line, we make it parallel to the dislocation line. So the Burgers vector and the dislocation line are parallel. Now the region that is slipped is the region to the right of that dislocation line in the figure. If I move that screw dislocation perpendicular to itself, I increase the area that is slipped. If I move it far enough to push it all the way out of the crystal, I create exactly the same slip that I got with the edge dislocation. Only this time, in this case, I'm moving a screw dislocation across the width of the crystal rather than an edge dislocation along the length of the crystal. The consequence is the same. What about these curved dislocations, which is what most dislocations really look like, as you saw in the indentation? Imagine a dislocation loop like this. A region on the plane has been slipped that is confined by this curved boundary. The dislocation is the boundary of the region that is slipped. So the whole boundary is a dislocation. At the back and front in the figure, the Burgers vector, the region of slip, which is constant over that area, is perpendicular to the dislocation line. So if I examine the situation here or here, I see an edge dislocation. On the sides of that region of slip, the Burgers vector, the slip vector, is parallel to the dislocation line. So if I examine the dislocation here or here, I would see a screw dislocation. In between, and in fact for the overwhelming majority of the circle that I've shown here, the dislocation loop, it's what's called a mixed dislocation. It's neither edge nor screw, but in between. Most of the dislocations you actually see in materials in the real world are curved, irregular in shape, and they are mixed dislocations. Neither simple edge nor simple screw. There are circumstances in which you can kind of force a dislocation to be a pure edge or a pure screw. But in deformation, most of the linear defects you see are neither edge nor screw, but somewhere in the middle. Okay, how does this perform? Better than the next? No. Okay. So what happens here? Suppose I now move this dislocation perpendicular to itself. Moving a dislocation parallel to itself does nothing. Moving it perpendicular to itself will expand the region that is slipped. If I expand the region that is slipped, I'm deforming the material. And if I expand this circle, this dislocation loop, until it actually moves out of the crystal, what I will wind up with is this once again. The whole top of the crystal displaced with respect to the whole bottom of the crystal by the Burgers vector B. So it doesn't matter whether I move an edge dislocation, a screw dislocation, or a mixed dislocation, or a dislocation loop. What physically is happening is that the material inside the dislocation, behind the dislocation, has been slipped by the Burgers vector B, and moving the dislocation perpendicular to itself just expands the area that has been slipped by precisely that Burgers vector. So whatever the shape or configuration of the dislocation, if I move it completely through the material, I get exactly the same slip. The top slips over the bottom by the Burgers vector B. And that's what's going on in plastic deformation. Well, it is important to remember, and of course one of the things that we noticed about dislocation plasticity in a very early stage is that these slip lines do tend to be very planar. There's a good reason for that. If I take an edge dislocation and imagine it to move, there are two different ways that it can move, and they differ dramatically in their difficulty. The first way to move it is dislocation, what we call dislocation glide. If here's the edge dislocation, to move it forward by one step per plane that it penetrates to move it forward by one step in this two-dimensional cut, all I have to do is break, well, where am I here? I have to break this bond and establish that one, in which case I move to the configuration on the right here. that is a relatively easy process because it only requires breaking and reestablishment, reconfiguration of a very, very few local bonds. In particular, 2 bonds per plane that the dislocation threads through. That's called dislocation glide. And in an edge dislocation, that makes movement in the glide plane, which is the plane that contains both the line and the Burgers vector, the one shown here, relatively easy. If I try to move that dislocation out of the glide plane, I have a problem. If I want to move it up, I have to get rid of atoms. The only way to get rid of atoms here would be to have a vacancy, a vacant site out here, diffuse and get onto the dislocation line in this position. Alternatively, if I want to move the dislocation down, I have to add atoms. The only way to add atoms is add them from the surrounding of the dislocation and eject vacancies. So I have these processes which involve climb, which are called climb, always involve either the addition or subtraction of material. As a consequence, this process is relatively difficult. So if you look at an edge dislocation, it can move easily in its glide plane, only with difficulty out of its glide plane, and that's the basic reason that slip is such a planar process at low to moderate temperature. When you get to high temperature, for reasons we'll discuss later, this climb becomes a bit easier, and there we actually begin to see much more of these irregular movements of dislocations. Now, if you turn around and look at a screw dislocation, in a screw dislocation, the Burgers vector and the dislocation line are parallel. So a screw dislocation can in fact move in any plane. It's not confined to a plane. However, when you go to real materials, almost all dislocations are mixed. They have at least some edge character. And as soon as the dislocation has some edge character associated with it, it has a well-defined glide plane. So in almost all cases when you're deforming a material, you're moving dislocations by dislocation glide with a glide plane that is determined by the edge component of the dislocation that's moving. So that's why the slip is almost always planar, unless you get to rather high temperature, as we'll discuss later. Okay, that's basically what we need to know about dislocations at this point, line defects. So let's move to the next stage of things, which are surface defects. Surface defects are the external surface. They're also internal surface defects, as we'll see. Let's look first at the external surface. If you have just a free surface of a crystalline solid that's in contact with, in fact, any solid at all, applies equally well to amorphous solid, you'll discover a situation that looks something like this. The surface is a region of high energy. It has associated with it a surface tension, which is, if you want, it's a thermodynamic definition, but essentially it's a surface energy, which is always positive. Surfaces always have positive energy. The surfaces are also chemically active. Well, they have structure. In this case, you see a very simple structure because the surface is parallel to a close-packed plane of the atoms. But in general, they also have a chemical structure. You will have, for example, if there are solutes in the solid, and there always are, some of those solutes will tend to segregate to the surface, giving you an aggregation of material something like this. From the vapor, atoms will be adsorbed on the surface, segregated to the surface. Molecules will be adsorbed on the surface, something like this. If you happen to be in chemical engineering and you're concerned about catalysis, this is a critical process in catalysis, the adsorption of things on surfaces. So we have a surface tension, which is always positive. The chemical state of the interface, there are adsorbed atoms or molecules. There are segregated atoms, which may come from the interior and segregate to the surface. It's a consequence of the second law of thermodynamics, which we may or may not discuss later, but just let me tell you that it is, that any change that happens spontaneously at the surface always lowers the interfacial tension. Classic example of that, when I was a kid, and maybe not as nice as I should have been, where I was growing up in the deep south, we had these, called them pond skimmers. They're little bugs that would sit on the surface of the water, and they would ride the surface tension, and they could move really quickly across the water. But we discovered a trick fairly early. If you took a bunch of these bugs and you put them in a little bucket, and you took a bar of soap and you put it in the bucket, all the bugs would sink and drown. What's happening, of course, is that the bugs are using the tension of the water as a surface to ride, to stand on. If you put soap in the water, the soap immediately goes to the surface, it lowers the tension, down go the bugs. And we were terribly cruel to those bugs, I feel guilty about it every day now. In free surfaces of metals, well, in fact, in general, but particularly in metals, the surface tension is always lowest for some low-index plane. Simply because the low-index planes are the planes, by that I mean the planes that are closest packed, I should say that. The closest packed planes are the planes that have the fewest dangling bonds sticking out from them. And since the surface tension is in a very crude way proportional to the number of dangling bonds, the more close packed the surface, the fewer the dangling bonds, the lower the surface tension is going to be. That is reflected not only in the tendency for metal, for virtually anything, to have a densely packed surface, but even if we have a surface that we force to be slightly off the close packed direction, say the 111 plane in a simple metal, what you will tend to find is a surface structure in which you have ledges that are close packed, which you have planes that are close packed divided into ledges, something like that, so that as much as possible of the surface still constitutes a close packed plane. Most real surfaces, particularly in metals, will be almost close packed planes with steps and ledges going out across the surface. Again, if you happen to be concerned about catalysis, this is a big deal, because the edges of these steps are places where an adsorbed atom can bond to more than one atom on the surface. And as a consequence, adsorbed species like to be in places like this. Therefore, if you're trying to make a surface active so that it will be catalytic or something of the sort, you do pay attention to the surface that you have provided so that you control the number of steps or edges and therefore the activity of the surface. In metals, if you get up to a low temperature, metal surfaces tend to look something like this, pretty well organized. As you get to higher temperature, for entropic reasons, the interface becomes much less regular, much more disorganized, and becomes very rough and diffuse, something like this. And that's just, of course, if you raise the temperature, the second law of entropy always drives you toward disorganization, and it pertains to surfaces as well as to